Welcome students. So we will continue our lectures of digital communication. So in this lecture we will go through multiple random variables. So in your previous lectures we covered the theory of probability and the concept of random variables and random processes, and we talked about the CDF and PDFs of a single random variable. So now we will see that if we have a joint random experiment or a combined random experiment where multiple random variables are involved, then how to represent them through joint CDFs and joint PDFs. So basically you have two random variables instead of one, so x and y, and they can take the corresponding values small x and small y. Basically the CDF, or the cumulative distribution function, is defined as the probability of the random variable x taking a value less than equals to small x, and simultaneously the probability that the random variable y taking a value less than equal to small y. So this is defined as the joint cumulative distribution function. So earlier you saw for a single variable, if you just off one of the variable in this expression, then you will get the expression for the single CDF. So earlier you were seeing that for f of x small x, this was probability x less than equal to small x. So that was the case for single random variables. So now that you have multiple random variables, that is denoted by this expression. And basically when you have a comma like this, so this means that so x less than equal to x comma y less than equal to small y, this means that x taking value less than equal to small x and or the intersection of the case where y takes value less than equal to small y. So this is the scenario here. So when we have a comma, basically this means both happening together, that x takes a value less than small x and y takes a value less than small y. And similarly for joint multiple random variables, we can define PDFs. So the PDF in this case is the double derivative here. So basically in case of a single random variable, let's say when you are saying f of x, that was basically the derivative of the cumulative distribution function of the single random variable with respect to x. Here in this case, since we have two variables x and y, we are taking the double derivative with respect to x and y of the joint CDF, and then we are getting the joint PDF here. So, and one assumption goes here that to take the double derivative, this function, the CDF, the joint CDF, has to be continuous everywhere within the range of x and y. So this comes from the basic properties of derivatives. A function has to be differentiable, and to be differentiable, the function has to be continuous within its entire range. So this is the condition that also needs to be fulfilled. So if we have joint PDFs, then surely we can also have marginal PDFs also, and the marginal PDFs can be obtained from the joint PDFs in this manner. So if you take the integration of the joint PDF over all values of x from minus infinity to plus infinity, then you will get the marginal distribution or marginal PDF of the other variable y. Again, if you take the integration with respect to all values of y, then you will get the marginal distribution of x. And if you integrate with respect to both the variables over all possible values, then that integration gives you the entire sample space, the entire joint sample space, and therefore that gives the value 1. So that is basically this particular quantity, which is the joint CDF of x and y calculated at the points infinity. So basically this is nothing but spanning over the entire sample space of x and y, and that definitely will give you 1 from the basic postulates or basic properties of probability theory. And if any of the variables x and y are set to minus infinity, or both of them are set to minus infinity, then this, as you know, is an impossible event, because both the random variables x and y would take real values, and that has to be within minus infinity to plus infinity. So you cannot have a value less than minus infinity. So if you set minus infinity as one of the limits, then that will give you an impossible event, and that will be 0. So similar to single PDFs, joint PDFs have the property that they are non-negative for all values of x and y, and the total volume, or in other words the double integration of the joint PDF with respect to both the variables, will give you the value 1, because that spans the entire sample space. And the marginal densities, as you saw, as obtained in the previous slide, they has to be, these marginal PDFs also has to be valid PDFs with the property of a PDF that it should have. So we can define conditional PDFs also when we have joint distribution. So we can define conditional PDF like this. What is the conditional PDF of the random variable y given x? So that can be defined in this manner. So this is again quite similar to the Bayes rule that you saw in the previous lectures. So basically you have on the numerator the joint PDF of x and y divided by the marginal PDF of x, provided that this PDF is non-zero, if x is non-zero. You can similarly define the marginal PDF of let's say x given y in the same manner. So you can say that this will be f of xy as numerator, and then in the denominator this will be f of y. So in this manner you can define the the conditional PDF of x given y. And if this conditional PDF of y given x does not depend on x, and it gives you the marginal PDF of y, so whether you condition y over x or not, it gives you the same, then this means that x and y are statistically independent. And if this holds, then from this equation this will also hold. So this is the condition of statistical independence, that the joint PDF of x and y is equal to the product of the marginal PDFs of x and y. So similar to the moments of single random variables, you can also define joint moments when you have multiple random variables. So general expression for the joint moment is given by this. So this is basically expectation of x to the power j and y to the power k, which means the jth moment of x and the kth moment of y, that is generally defined as this expression. So you multiply the values of x and y raised to the corresponding power j and k, and then you multiply it with the joint PDF and then integrate it over all values of x and y. You can also obtain the joint central moments by this method. So you subtract the means from the corresponding random variables and then raise it to some arbitrary powers of j and k, and then you can have the similar expression. The only difference is that here you are multiplying with x minus the mean of x to the power j multiplied with y minus the mean of y to the power k, and then the joint PDF, and then you integrate it over all values of x and y. So you can get the special cases from these general cases. So if you set j and k equal to 1, then you have this joint moment. You call it correlation when j and k is set to 1, and it is defined as this. And then also you can have the covariance, which is the joint central moment when you set j and k equal to 1. So now we will go to the concept of discrete memoryless channels. So far we were discussing probability theory and random variables and random processes. So now we will slowly migrate to the concepts, to the actual concepts of digital communication. And the first thing that comes is the discrete memoryless channel. So let's see what it is. So let's say we have a channel which is basically a medium through which you are communicating your messages. So there are some input to the channel and then there are some output. Let's say the input is taken from the alphabet x1, x2, x3 up to xm. So the input is defined by a set capital X, which contains different values x1, x2, x3 up to xm. So m values. So it's an m valued alphabet. So this can be ones and zeros. This can take any value. This can be A, B, C, D, just like the English alphabet. This can be any value. So x1, x2, x3 up to xm, and they are communicated through this channel which lies in between. So this is your channel, and all the input alphabets are communicated through the channel, and you get a corresponding output alphabet set y, which consists of some discrete symbols y1, y2 up to yn. And the channel does nothing but maps these input symbols, that is part of the input alphabet, to these output symbols which are the part of the output alphabet. and the mapping from the input symbols to the output symbols are determined by this transition probabilities. So see, these are all conditional probabilities that you learned in your previous lectures. So basically this means, like, if x1 was transmitted, then what is the probability that you obtain y1? Okay. Again, if x2 is transmitted, then what is the probability that you receive y1 at the end of the channel? So these are the significance of this probabilities, these conditional probabilities, and these are called transition probabilities. Okay, so the entire channel, the discrete memoryless channel, is defined by a set of inputs, a set of outputs, and a set of transition probabilities that map the inputs to the outputs. And you can note that for any j, okay, if you sum over all the k's here, so let's say if your transition probabilities are of the pattern probability yk given xj, where your k varies from 1 to n, 1 to capital N, and j varies from 1 to capital M. So for any j, if you sum over all values of k, the transition probabilities, you will get 1. Okay. So this is the property of the transition probabilities. So this is a general case of a discrete memoryless channel. Now there are few special cases. So in the general case we have m inputs and n outputs. Now if you have, let's say, 2 inputs and 2 outputs, then we call it a binary symmetric channel. So you have the input alphabet which consists of 2 symbols x1 and x2 that can be equal to 0 and 1, and then in the output also we have 2 symbols y1 and y2 which can again be equal to 0 and 1. So basically that's why it's called binary, because the input and the output taking 2 values, and it's symmetric also because both the inputs and the outputs are same number. So you have 2 inputs, 2 outputs. So that's why it's a symmetric channel. If you had, let's say, 2 inputs and 3 outputs or something of that combination, 3 inputs, 2 outputs, then that wouldn't be called a symmetric channel. So basically it's binary because the inputs and outputs take 2 values, and it's also symmetric. And the transition probabilities here are defined as p and 1 minus p. So if you are transmitting x1, then with a probability p, it can get flipped to y2. So x1 is 0 and y2 is 1. So if you are transmitting a 0, there is a probability p that after getting transmitted through the channel, it can change to 1. So that is basically an error. So the probability of error in this case is p, and with 1 minus p probability you can get the same symbol at the output. So this is the property of the binary symmetric channel. And p and 1 minus p, this thing is a direct effect of the previous relationship here that you saw. So basically all the transition probabilities, if you sum them over all values of the output k equal to 1 to n, then that should give you 1. So basically in the case of binary symmetric channel, if you sum over all the values, so basically you get p plus 1 minus p, and this gives you 1. So basically that condition holds. And also one thing to note, like if your p is less than half, then the channel makes sense. So let's say if your probability of error is less than 50%. So ideally you should have this probability as low as possible, but if it is less than 50%, you can say that it makes some sense. So you are transmitting a 0, and with, let's say, 30% chance that that 0 is transmitted as 1. Okay, so with 70% chance you still have the option of getting it right. Again, if the probability of error is very high, let's say p equal to 70%, then also you can say that, okay, since my probability of error is so high, if I get a 1 in the output, then there is a chance that there is a 70% chance that it was a 0 which was sent. So that then also you can make a decision that, you know, my input was 0, so if I am receiving a 1 with 70% probability, or in other words, you just relabel the outputs. Okay, but if your p is exactly half, then the channel is of no value, channel is useless, because then in the receiver, if you receive a 0, then you cannot make a decision what was transmitted. You have to toss a coin. So it's basically as good as tossing a coin and guessing the input. But if your p is less than half or more than half, you can make a right guess what was the input by observing the output for maximum number of times. So that's the whole concept here. Now we can also have a binary eraser channel. So in this case you have same 2 inputs and 2 outputs, but there is also a third case where you end up having an output symbol which is equal to E, and E is called an eraser. Okay, so you are transmitting x1 and x2, which are equal to 0 and 1 respectively, and you can get the same values in the output with probability 1 minus p. So usually p is very small, so 1 minus p is very high. So with a very high probability you will get those values that you transmitted, but there is also a chance, a small chance, that you will end up in the state y3, which is an eraser. So these are the 2 special cases of a binary of a discrete memoryless channel. The binary symmetric channel is one of them, the binary eraser channel is another. So now let us analyze the discrete memoryless channel using the concepts of probability theory that we learned. Okay, so let's say you have your inputs x1, x2, x3 up to xm, and each of those inputs are denoted by xj. So there is a probability associated with those inputs. So let's imagine that those symbols are generated from a source, a symbol generator, and each of them has a probability p of xj, okay, of getting generated. Okay, so that probability is called a priori probabilities. Okay, and then you have the transition probabilities, as you saw, which is the property of the channel itself. So the probability that you receive yk given xj was transmitted. Then you can define the joint probabilities of xj and yk using the rule, using Bayes rule. Okay, so basically probability of xj comma yk is equal to the a priori probability of xj times the transition probability of yk given xj. So now if you sum these joint probabilities over all values of xj, of all values of j, then you can get the marginal probability of yk. So basically, if you have a joint probability distribution as you saw previously, and if you sum it over all values of one variable, then you get the probability of the other variable. Okay, so if you sum the joint probabilities for all values of xj, you get probability of yk, and and then this joint probability is given by this value. So you replace the joint probability of xj comma yk with probability of xj times the probability of yk given xj, and the same summation is here. So so now so this is how you obtain the yks, the probability of the outputs, each and every output from the input a priori probabilities and the transition probabilities. And you also note that the if you sum these output probabilities over all values of k, then you will get 1. Okay, now let us define the a posteriori probabilities. Okay, so a posteriori probabilities is probability of xj given yk. So a priori probability is here, probability of xj, and the transition probabilities are here. So transition probability is yk given xj, and a posteriori is basically, if you flip the roles here, so xj given yk. Okay, so this can be again written as the joint probability divided by the probability of yk, and the probability of yk you have obtained here. So you can write that down here, and you already know these values. These values are given by this expression here. So you can easily calculate the a posteriori probabilities. So what is the probability that xj was transmitted given that you observe yk at the output? So basically this is just flipping the role here. So this represents the probability that xj was the input given that we have observed yk at the output. Okay, so this is the a posteriori probability. So so moving on, we will keep analyzing the discrete memoryless channel. So now let us ask a question to ourselves. So suppose yk is observed at the output, and you are trying to decide that what could have been the possible inputs, and you want to make a correct decision, or in other words, you want to make an optimum decision. You don't want to make mistakes. Let's say you observe the yks 100 times, and 80% of times or 90% of times you want to make a correct decision, that given that yk is observed in the output, what was the input symbol that was transmitted. And if you make the correct decisions 80 to 90% of time, then that is basically the optimum decision rule. So you have to find out that optimum decision rule. So what is that rule that maximizes your guess, or that if you are guessing the input by just observing the output, what will maximize your guess, or in what way you will make the correct guess most number of times. So to do that, we basically again use the concepts of probability theory. So basically, the optimum decision rule is defined as follows. So let's say you observe yk, okay, given the observation is yk, what is the most likely transmit symbol xj, and that you define as x hat. So so x hat is nothing, or is equal to that value of xj which maximizes this probability. So this is defined mathematically as argmax. So the notation argmax means the argument which maximizes a function. So basically, what value of xj maximizes this probability? So if you look into this probability of xj given yk, this is basically the a posteriori probabilities, as you saw in the previous slide. So this is the a posteriori probability, and the a posteriori probability is a function of xj. So if you observe this function, this a posteriori probability over different values of xj, so let's say if you let's say if you tabulate the values of xj here, let's say different values of xj, okay, and you observe the values of probability of xj given yk, then you will let's say xj can take m values, as so x1, x2 up to xm, and you find out the probabilities of this of x1 given yk, x2 given yk, up to the probability of xm given yk, and then you see which values of xj gives the maximum value of this probability. So let's assume, let's say for x2 the value is maximum. So let's say all these values are observed, and let's say for x2 this probability is maximum. So that means your x hat will be equal to x2, okay, according to this optimum decision rule. Or in other words, the most likely value of x that was transmitted, given that you observe yk at the output, is that value of x which maximizes this a posteriori probability. So if you see that x2 maximizes this value, then probably your optimum decision rule will be x hat equal to x2, because x2 maximizes this a posteriori probability xj given yk, okay. So whenever you observe yk, you can make a guess that x2 was transmitted, and if you observe, or if you perform this experiment hundreds and thousands of times, you keep observing the output of a discrete memoryless channel, let's say 1,000 times, and whenever you observe yk, or let's say you observe yk all the 1,000 times, then if you make a guess that the probable input was x2, then you will be right maximum number of times. So this is why it is called optimum decision rule. Okay, and the optimum decision rule is nothing but it's that value of the input which maximizes the a posteriori probability. So this is the fundamental behind the optimum decision rule, and you can also do it from a different perspective. So there can be an alternative decision rule as well. So you can say that your optimum decision rule is that value of xj that maximizes the transition probability. So the transition probabilities are given by probability yk given xj, and you do the same exercise again. You observe this probability for different value of xj and see what value of xj maximizes this probability, and you can set that value equal to x hat, and then that is also another decision rule. That decision rule is called maximum likelihood decision rule. What we discussed in the previous slide was maximizing the a posteriori probability. So that's why it was called maximum a posteriori decision rule or MAP rule, and this one is called maximum likelihood decision rule or ML decision rule. And both rules are equivalent if the transmit symbols are equiprobable, or in other words, if all your probability of xj's are equal to 1 over m for all j equal to 1 to m. So if you try to calculate the probability of error, you will see that the map decision rule is actually minimizing the probability of error. Okay, so we will show this. So in another video that will explain you in more detail with a specific example.